Oh, we gotta go fast. Okay. We're going to go through this fast because there's a lot of them. But I wanted to give you more than less. So, energy, resources, and conservation. This is mostly what it's going to focus in on is fossil fuels, nuclear power, and alternative fuels. So those are the three things you need to know out of this section for the most part. Basically, oil skyrocketed in the 1970s because Israel, remember there's a lot of politics. So, yeah, hand these out for me. Sorry. Yeah, hand those out. We sided with Israel in the 1970s, who were at war, disagreement with the Arab countries. And because of that, the Arab countries put a squeeze on us and didn't want to give us a lot of oil. So that's why prices skyrocketed. That's why compact cars came out. The Japanese cars became popular, or started to become popular. It was back then in the 70s, I believe this is the case, Japanese products were considered inferior to U.S. products and European products. So it was, but Japan knew that there was an oil problem, and so they started coming out with cars that didn't, consume as much gas. So that, because of the oil prices, people started buying Japanese cars a lot more. And then U.S. cars, Detroit was making cars that were too big, the gas guzzlers and the muscle cars like that. They were taking too much gas, and people couldn't drive them anymore. So
I sold Buicks in 1972. They averaged 8 miles to the gallon. I was a car salesman.
Bad time to sell those cars. So there was an oil embargo in 1979. In 75, Ford signed an energy policy and established Strategic Petroleum Reserve, which put 1 billion barrels of oil in salt caverns near the Gulf of Mexico in case of emergency. And they're still there. We don't talk about it very much, but if there was an oil problem, they could pull and draw from those oil reserves to balance out the price of oil if the Arab countries were to totally cut us off or something like that. Of course, we're trying to find out new technologies to reduce the amount of oil we use. But if there was a really big problem, we actually have hidden oil reserves that, but the public doesn't really know about. Last big oil crisis was in 1990 with the Persian Gulf War. I think you guys remember. I think you're old enough. When they used to have the air, I forget who set it on fire, but they would set the oil wells on fire, and see these oil wells like spewing out fire.
What's the movie? Jarhead. There you go.
Yeah, I remember. Yeah.
And they're burning the oil wells, and you see the whole, and it's raining oil.
Yeah, it's raining oil and salt, soot, and ash and stuff. That wasted a lot of oil, but. This is just a graph. You should be able to read this graph and understand what it is. It's the price per barrel goes up and then down. Just depends on what's happening. And they may not give you this sort of stuff, but you should be able to know what's happening in history and why the oil prices are going up or down, things like that. So, like I said, in class, you should always be able to determine whether something's, what's going on in history. Is there a plague? Is there a war? Is there oil crisis, what's going on that may cause something to happen in that graph. So you should be able to interpret that. So they probably won't give you that information. Just, you need to know a little bit about history for this. 20% of the world's population live in highly developed countries. 60% of the world, they use 60% of the oil. So the 20% of the world, you can read it. So that means we use 8 times much oil per capita or per person than in developing countries. There's North America. We use energy than these other countries. This is energy in years. This is an easy graph to figure out. Fossil fuels. Fossil fuels are composed of partly decayed remnants of organisms. See if I can find something. Sorry, going off camera. I actually just got something in the other day. I hope I can show you. Okay, I can't find it. But anyway, I had gotten a piece of the different types of coal that I wanted to show you, and oil shale, so you can see there's the anthracite and the bituminous and stuff like that. So fossil fuels are non-renewable resources. Coal. Old plants and ferns and moss from carboniferous swamps fell into the water millions of years ago. Fungi and bacteria that normally decompose the organic material couldn't do their job in the water. Dirt fell on top of the underwater. Heat and time turned the carboniferous swamp into coal. So there's a carboniferous swamp. That's coal. Oil. Dead organic microscopic organisms accumulated on the bottom of the ocean floor. Fungi, bacteria that normally decompose the organic material couldn't do their job in the water. Dirt fell on top of the aquatic microscopic organism, created sedimentary rock. The pressure from the rock, heat, and time turned the aquatic microscopic organisms into oil. Notice it's almost exactly the same. The difference is the first one, coal, is made out of plants. The second one, oil, is made out of dead organic microscopic organisms, but they were formed the exact same way, working exactly the same way. So that's a dead microscopic organism. Black coal is in the word for oil, so it turns it into oil. Natural gas, sea oil, it's formed the same way. Natural gas floats on top of the oil bed because it's less dense. And natural gas is mostly methane. So methane comes from the decomposing organic microscopic organisms. Hey. And it also comes from your body. So right when Miss Daniels walks in, I'm going to talk about flatulence. So it comes from when you fart. And we actually use that in our decomposing stuff in our bodies, and also when we throw things away. We make methane and we can burn it. Coal became the dominant fuel in the 18th century. Before that, the dominant fuel was wood, and it's still used as the dominant fuel for industry and utility companies, especially utility companies. So most, Most energy companies, electric companies, make their electricity by burning coal. There's 4 grades of coal. I was going to show them to you, but I can't find them right now. Lignite, which is the softest, and this is also the most polluting. Whoops. And then the other 3. Anthracite is the hardest. Bituminous is the most abundant, easiest to mine, but contains the most pollutants, i.e. sulfur, other than lignite. We don't use lignite because it kind of falls apart in your hand. It's found on top of the ground. Anthracite is the hardest, most expensive to mine, but contains the least amount of pollutants. If you burned a thing of anthracite, a hunk of anthracite, it would burn a lot longer than the bituminous. Bituminous burns out quickly. Anthracite takes a long time. And charcoal is not made of coal. It's not the same thing. Charcoal is coal powder mixed with wood chips and then formed into little charcoal briquettes. So there's lignite, bituminous, and anthracite. So this is the softest. We don't really use that. To the hardest. It's on your sheet. This is the hardest. Most coal reserves are found in the northern hemisphere, and they occur in strips between rock. Strip meaning horizontal strip, not strip. So there's rock, then coal, then rock, then coal, then rock. There are 2 types of coal mining. There's surface or strip mining, where they blow up all the surface, they move it out, and then they dig up, blow up the coal, collect it, then they blow up the next layer, then they blow up the next layer, so they go down farther and farther. That's really, really bad for the environment. So surface coal is embedded in less than 100 feet below the surface of the Earth. 60% of the coal in the U.S. is surface coal. Subsurface coal is deeper than 100 feet. 40% of coal in the U.S. is subsurface. Surface coal is the lignite and bituminous. Subsurface is the anthracite. And most of the coal is found in the whole world is found here. And if the world relied on coal for fuel rather than oil, we would be probably the richest country in the world because we have the highest amount of coal. Either the highest or the second highest. But we don't have much oil. We used to have oil in Texas, but it's almost all gone. But if we relied on coal, and things used coal, and we made coal prices high, we would be rich. Surface mining is easiest and cheapest, but harms the environment the most. In the 20th century, 90,000 American coal miners died in mining accidents. There's something called black lung disease, which they get from breathing in coal dust. 2,000 miners died from this a year. In 1977, Surface Mining Control and Reclamation Act was passed. That meant that after they dig for coal, they got to put all the dirt and stuff back into the coal mine. They can't leave the coal mine empty. That's what this is all about. And that cookie was the lab we were supposed to do. Alright, burning of coal produces a lot of carbon dioxide, which, as you know thoroughly, is the main greenhouse gas that causes global warming. You should know global warming. Burning of coal, especially bituminous coal, which is the softer one, easiest one to get to, releases the other pollutants, sulfur oxides and nitrogen oxides. Sulfur and nitrogen oxide cause acid deposition, which we talked about in the last PowerPoint. Acid deposition is the same as acid precipitation, but also contains dry acid particles, so it could be ash. Clean Air Act amendments of 1990 require the nation's dirtiest coal-burning power plants to cut sulfur emissions by 1995. They did. Most coal-burning power plants use scrubbers to remove the air pollutants. The byproduct of scrubbers, well, CO2 is still let out, but all the other ones are collected. And the stuff that's left over after the scrubbers scrub the stuff coming out of the coal plants, is used to make wallboard. So in manufacturing, it's used to make the walls, basically. This is called resource reclamation. So the use of sludge, or it can be anything, a byproduct of something used for something else, is called resource recovery. Stupid example, but it just popped in my head. In Japan, they like their faces to be white. In the US, we like to be tan. But in most places in the world, people like to be white. The lighter your skin, the richer you're perceived. Because people who are outside working in the fields are considered the poor people. And if you're inside and have an inside job, you're considered more wealthy. So people want their skin to stay light because that they don't work outside. A lot of cultures believe that. The U.S. is one of the few cultures that believes the opposite. We believe that, for the most part, that going outside getting a tan means health and vitality and stuff like that. But that's not true in other countries. But the point is, in Japan, they sell this very expensive powder that you mix with soap. And I actually used it once. That's how I know about this. And this would be considered resource reclamation because what the powder is it's just dried finch poop. And what you do is you take it, you mix it with soap, you wash your face with it. It smells kind of like a weird peanut butter smell, but the reason you use it is it bleaches out and lightens your skin up and takes away any freckles, things like that. I use it twice, and I don't use it on a regular basis. And it costs something like $200-300 an ounce for bird shit. Excuse my language. Okay, bleep that one. That's how I talk in class normally. Bleep that too. But so that would be another example of resource reclamation or recovery, is using the leftovers of something else or the byproduct of something else as a main source of something. So in this case, it would be a cosmetic. Because of uric acid, it bleaches your skin out. All right. Fluid bed combustion is crushed with coal, limestone, much easier to burn than coal itself. That's how one works. You don't need to know that in detail. Up until the 1940s, coal was a predominant fuel source. Now it's oil and natural gas, and that's 60% of the world's energy. Petroleum and crude oil can be refined into gases, gasoline, heating oil, diesel. It can be made into lots of stuff. It can be made into clothes like polyester. It can be made into a lot of cosmetic products. They put it in shampoo. They use it as moisturizers. A lot of stuff. Baby oil is just mineral oil, which is a petroleum-based oil. So stuff that you put in your baby's butt, or a lot of bases for tanning lotion and oil is also petroleum-based. That's the stuff that causes zits. When it says it's non-cosmogenical, that means it's natural, it's plant-based, and it won't clog your pores. But there's a lot of tanning oils out there and oils that you can use for moisturizing that are petroleum-based. They feel really good because they make your skin soft, but they'll clog your pores and you get acne if you use them because your skin can't breathe with that oil on top. So you can actually make that out of petroleum also. It can be used to produce petrochemicals, which are used to make fertilizer, plastics, paint, pesticides, polyester. Natural gases, methane, ethane, propane, and butane are used for heating and cooking. Natural gas use is increasing in the generation of electricity, transportation, and cooling. The main disadvantage of natural gas is that it's found far away from where it needs to be used for energy. And it takes 4 times as much money to transport natural gas than oil. So natural gas is found in oil reserves, but then they've got to transport it to where it's needed. So what they do is, because it's so expensive, instead of using that natural gas, they re-inject it back into the oil well in the hope that someday we'll figure out a way to transport natural gas cheaper, and then we'll use it. Right now, they just put it back into the ground for the most part. So most oil well locations, remember oil and natural gas are found in the same place, re-inject the natural gas back into the earth rather than transport it for use. So they would have to cool it down. Remember, gas that's cooled can turn into a liquid. They cool it down enough, then they can transport it as a liquid. You can pressurize it. You can do a lot of different things to it. But it's expensive and can be dangerous if you do that. Oil and natural gas are found in structural traps, and they're near salt domes. So this is an example of an oil well. So the oil is here, and the natural gas floats on top, because obviously gas is less dense, but it's locked in by the rock. Here's another type. Here's one with a salt dome in it. A lot of times they're found around salt. This one doesn't have any natural gas. Sometimes they just have oil. Most of the world's oil is found in the Persian Gulf countries, 65%. Most of the world's natural gas is found in Russia, 33%, and Iran, 18%. The reason they're not together is, the reason they're not all found in the Persian Gulf countries is because some oil wells don't have any natural gas. And some oil wells have more natural gas than oil. So in Russia, those oil wells have more natural gas. And the US and Canada have coal bed methane, which is a natural gas associated with coal deposits. So like radon that comes out of near coal deposits, so does a certain type of methane gas that we can use. New oil deposits have been found on the edge of the continental shelves, and we have to use offshore drilling to access these. That's something important. Right around the time that this current AP test was written was right when the Gulf of Mexico oil issue happened with BP. So they probably will ask you a question on the BP oil crisis, because it happened right before they wrote the test. And so they like to use current events. So know a little bit about the oil leak in the Gulf of Mexico, all right? So they might ask you questions. How might they spend? What would be a benefit? What's an environmental detriment? That's pretty simple. What economic effects could it have? What environmental effects could it have? List two or discuss two something. Remember, if they say two, only do two. Don't do three. They're not going to look for your best answer. They're going to look for the first and second answer. But that's a possible. That and the earthquake in Japan affecting nuclear power plant and the earthquake in Haiti are possible current event topics that they might discuss. So know a little bit about those topics so you can sound intelligent when you write your essay. World's major oil producers are not the major oil consumers, so Persian Gulf countries don't use very much. US and Europe use 50% of the oil. Persian Gulf countries use only 5% but produce 27% of the oil. By 2015, the US will import 100% of its oil. There's right now, another thing they could talk about, because this came around the time that they wrote this current AP test, is the oil found in Alaska under the National Wildlife Preserve. What's the difference between a reserve and a preserve? If you have a wildlife refuge or reserve, or a wildlife preservation or preserve.
Reserve just where the animals are, and preserve is where nothing can be touched.
Yeah, you can use the reserves you can use them for hunting and fishing and things like that, within reason. But the preserves, when they preserve something, you're not allowed to touch it at all. So that's in one of the, I think that's in the land and water use. Look at that. Wait a minute. Yeah. Oil combustion also produces a lot of carbon dioxide. Yeah, we can get through that. Okay. Don't worry about that. You don't have your book. There's different types of ways. There's syn fuels and other potential fossil fuel resources. There's oil shale, gas hydrates, coal liquefaction, gas liquefaction. So just read that on your own. That's tar sands. This is oil shale, gas hydrates. Those are methane. Is what that is. This is rock containing oil. The United States has a comprehensive energy policy. This is an energy strategy for the U.S. for several reasons. This is what our policy on oil is. The supply of fossil fuels is limited. The production, transport, and use of fossil fuels pollute the environment. And our heavy dependence on foreign oil makes the U.S. economically vulnerable. So that's a given. We're depending on the Arabian countries, Persian Gulf countries for a lot of our oil. So, if they want to raise the prices, they can raise prices, and that will cause us to pay more for oil and gas and stuff. The objective one for the strategy for the U.S. is increase energy efficiency and conservation. Objective 2 is secure future fossil fuel energy supplies. So they could say, well, you've got your reserve under Alaska. Why don't we just use that? Because that's going to give us 20 years. I think it's approximately 20 years worth of oil. So we could do that. That's an environmentally beneficial reason for using oil under Alaska. But the economic, it's an economic benefit, but environmentally it's bad, because then you're going to be drilling in a place that's supposed to be a preserve, where you're not supposed to touch the animals and plants, or wildlife at all, the environment at all, and then we're kind of breaking our own law by doing that. So it could be good because it can lower our oil prices, but it's bad because it messes up the environment. And remember, the environment and economy is like a scale. Most of the time, when one thing is beneficial, the other thing, it's a detriment, and vice versa. And in general, and this is a very generalized statement, that's probably leaked out too. In general, Republicans tend to go towards the economic side, they would rather do something to benefit the economy, while in general, I'm just saying it's a generalization, Democrats usually go towards the environmental side. So that's just a generalized statement. That's not 100%. And that's just something for you guys to know. Alright, objective 3, develop alternative energy sources. That's what we're trying to work on the most. That and reducing, reusing, recycling. 4, accomplish the first 3 objectives without further damage to the environment. That's our 4th objective. Nuclear energy. This is actually my favorite part, is nuclear energy. But we don't get to talk about it too much. So fossil fuels provide energy by changing the chemical bonds between the atoms, while nuclear energy provides energy by changing the nuclei within an atom. And you can create nuclear energy 2 ways: by fission, which is the way we normally do it, which is breaking a big atom apart into smaller pieces, or fusion, which is combining 2 small atoms together, and that theoretically can create a lot of energy or heat. The sun does fusion. We can do fusion. There are places where they do fusion, but it's so expensive and it uses so much energy to create that fusion that it's not beneficial to do the fusion, because you have to put more energy into it to get it to work. So they're looking to do cold fusion, right? Cold fusion, where that would basically satisfy the world's energy issues. So you're mixing hydrogen water, and hydrogen something, and lithium and water are a byproduct. So if we could do that, that would be really good environmentally, but we still haven't gotten to the stage where we can do fusion on a grand scale. So all the nuclear power plants are fission nuclear power plants. Conventional nuclear fission. This is the nuclear fuel cycle. So uranium mines and mills, you find uranium, you dig it up. It's kind of funny, I was watching a I Love Lucy special, and they went, and the government was paying people $500 or whatever at that time in the 40s, whatever, 50s, to find uranium, and they were just like digging it up with their hands, and thinking they didn't realize that it was bad for them and radioactive. And here they're walking around with all this stuff with a guy on camera, like, oh, look, that's I Love Lucy. It has nothing to do with anything. So after you find the uranium, you have to enrich it to uranium-235. So normally uranium comes as, I don't have my, what does it say over there uranium normally comes as? Is it 238? Yeah. Normally, when you average it all out, uranium comes in nature as uranium-238. They need to, quote, enrich it and change it to uranium-235 to make it usable for power plants and nuclear bombs, but you want to use it for power plants. It creates low-level waste. Then there's fabrication of the fuel assemblies. So they turn it into little pellets, and then they make these, put the pellets together into rods, and they put the rods together into these metal fuel assemblies. And that makes some waste. The stuff off to the right is the waste that's created at that level. Then you use those fuel assemblies in a nuclear power plant, and then there's some waste at every level. There's waste. And remember, what's the main waste from everything in life and in environment and everything? If you saw a multiple choice question, what would the answer be? Heat. You know, always choose heat if you see an answer. I mean, read the answer, read the question, but if you're not sure, choose heat. Spent fuel. So you've used the energy in the power, or they use the fuel assemblies in the power plant, and they temporarily store the spent fuel on site. So they keep it in special type of water, heavy water, for about 12 years, and then they take it out of there. It has to cool down, and they take it out of there, and then they store it in these barrels on site, like on the property of the power plant. So then they'll do spent fuel reprocessing. They do that mostly in other countries. They don't really do that a whole lot here. And they put them in what's called breeder reactors. But they don't really use that here. So once it's spent, it turns into plutonium and another type of uranium and something. What does it come in as? All right. Plutonium is one of the things that's a result of the uranium being broken apart and used. And then the idea is you want to stick it in a deep geological disposal. So the problem is we don't know what to do with the spent fuel. Right now they're kept on property and they're just kind of stored there temporarily. It's kind of like a hoarder. They just kind of put something somewhere and hope nothing happens to it, which is a very bad policy. They used to have Yucca Mountain in Nevada, but they closed that down. And the main reason they closed it down was because, think about it, if you have, there's a nuclear power plant right here. There's also one down here. And you would have to take this nuclear waste after it's been sitting around for 12 to 15 years and cooled down, literally cooled down. And you'd have to drive up 95 with it and then drive over here and drive through you can't fly it anywhere. You have to drive it into Nevada. Where's Nevada? I don't even know where Nevada is. Oh, over here to Yucca Mountain, Nevada. So if you have nuclear power plants, which are all over the United States, they're all transporting their nuclear waste to Nevada. Now, if you if you were governor of a state, would you want, say you were governor of Mississippi and Georgia, would you want Florida to be transporting very highly radioactive waste through your yard, through your state? No. Nobody wants that stuff put in their backyard. So, yeah. They're very wide. They've got lots of security, and people don't want those trucks going through their yard because if there's an accident, then the place is dead. Everybody's dead. It's too much radiation is released. Or there's a possibility, and there's a lot of movies about this. Terrorists could come in and steal this stuff while it's being transported. So you're likely to have somebody come in and try to take that spent nuclear radioactive material and turn it into a bomb, because you can use the spent fuel and make a really good nuclear bomb out of it. So there's a lot of issues why it closed down. So you can take the spent fuel reprocessing and re-enrich it to 235 again, or you can use it as is and make fuel assemblies again. But they don't do this in the U.S. They only do this in other countries like France, where they use the waste as the fuel for a new reactor. So the world's uranium, which is what nuclear power plants use as fuel, is found 21% in Australia, 18% is Kazakhstan. Just Kazakhstan. 11% is in the US, 10% is in Canada, 9% is in South Africa. Most of where it's found in the US is in the Midwest states, or Southwest states. It's usually found around in here. So East Coast we have coal, West Coast they have uranium. One uranium atom must be enriched to create isotope uranium-235 to about 3%. So in nature, you take a hunk of uranium. In nature, it's 1% of it is already uranium-235. But then they have to do something to it, and they have to enrich it in order to make it at least 3% uranium-235. So, and there's actually and those are the really highly protected places. uranium mines are not very protected. People know where the uranium mines are, but the enrichment plants, which there's 4 of them in the country that I know of, they're highly secretive. They don't let people know where they are, because if you know where they are, then terrorists can attack them, take the uranium, stick them in the enrichment machine. I don't know exactly how they enrich it, but they stick them in this enrichment machine and enrich it to make nuclear bombs. Uranium-235 is used in a nuclear reactor to create uranium dioxide pellets. One pellet, which is about that big, has as much energy in it as 1 ton of coal. So 1 ton of coal is the same amount of energy as 1 pellet. So the pellets are put together to create fuel rods, which can be up to 12 feet long. The fuel rods put together make fuel assemblies. This is what happens. During fission, the uranium-235 are bombarded with neutrons, which break apart the atoms into smaller pieces. The broken atoms release 2 or 3 neutrons, which hit more uranium-235 atoms, creating a chain reaction. So one hit creates like 3 to 5 hits, and those 3 to 5 create 3 to 5 for each one they hit, and so on and so on and so on.
There was a show on Discovery Channel of Science about like all elements, and for uranium they took like a clear cube and stuck all these mouse traps in, and they put ping pongs on. They threw one ping pong and it set off a reaction.
Yeah.
It's described like uranium.
Yeah, I showed you that. I showed you that.
I was pretty sure I watched it 2 years ago, maybe again.
Okay. I think I showed you that. I think it was Mythbusters. Maybe. I don't know. Anyway, yeah, it's a chain reaction. It goes on and on and on and on and on. And it's really hard to stop. Alright, the fission of uranium-235 atom creates a large amount of energy as heat, because remember, when you change one thing to another, whether it's a trophic level, whether it's energy conversion, whether it's change of matter, change of energy, whatever it is, when you change something, you're always releasing a lot of heat. So in this case, these little pellets create lots and lots and lots of heat. And that heat is used to create steam, and the steam turns the turbine, which creates electricity. All power plants work the same way. If you have a coal power plant, you're burning heat to heat up some water that creates steam, which turns the turbines, which creates electricity. In this case, you're causing the fission to happen, and it's creating heat in water. It's a little more complicated than that, but it spins a turbine. Steam spins a turbine, which creates electricity. In a natural gas power plant, they burn the gas, which heats water, which creates steam, which the steam turns turbines, which create electricity. So it's all basically the same mechanism, but the fuel is just different in different power plants. They all create steam that turns turbines. Alright, so steam turns turbines. There's actually 3-part water circuits in a nuclear power plant. Primary water circuit is water that's heated up to, I think it's something like 900 degrees. How can you heat water up to 900 degrees if it evaporates at 100?
You pressurize it like you do in a car.
Yep. You pressurize the water. So it's pressurized, and I think it's also deuterium or some heavy kind of water. It's not normal H2O. It's a different chemical version of H2O. But yeah, mainly that's the thing. You pressurize it, and if you pressurize the water, it'll stay as a liquid, and you can superheat it above 100 degrees. So it's usually heated between 5 and 900 degrees. And then that heavy water comes in contact with the fuel rods. Then that water, after it heats up, it goes into the secondary water circuit, which is not at all touching. The water from the primary doesn't touch the secondary at all. So it's like a metal, it's a heat exchanger, like a pipe going through a bigger pipe with water in it. So the little pipe's going to have it's going to be like a hot pipe. It's going to simplification, and it goes and heats up the water in the bigger pipe. The bigger pipe makes steam, turns the turbines, and then it goes to a third water heat exchanger, which cools the water down again. So you should read through this. Alright. It takes 20% of uranium-235 enrichment to 20% to make a nuclear bomb. Not that you need to know that. Breeder nuclear fission is the waste product of uranium-235, which is plutonium-239, and can be used as fuel again in a nuclear reactor. But we don't do that in the U.S. And you can use, there's breeder nuclear reactors all around the world. They use uranium-235, plutonium-239, and thorium-232 as fuel. And then they're reprocessed and used again. Is nuclear energy a cleaner alternative than coal? Yes or no? Read ahead. No, it's not. And here's why, so just remember that. Okay, is electricity produced by nuclear energy cheap? No, not really. There's why. Safety in nuclear power plants. Small chance, but it does happen occasionally. 3 Mile Island, Chernobyl, the thing that happened in Sendai, Japan. Sendai, right? Sendai, Japan. Yeah. Link between nuclear energy and nuclear weapons. You can read that. We like to change things into either vitrify them and turn them into glass logs, or turn it into MOX fuel, which can't be used for nuclear weapon. That's what we do in the U.S. Radioactive waste. Low-level radioactive wastes. There's a place in Washington State, South Carolina, and Utah that rent out space for other states to keep their low-level radioactive wastes, which again is a temporary solution. High-level radioactive wastes went to Yucca Mountain, and they can get rid of them in 3 ways. Underground in geologically stable site like Yucca Mountain. 2, in above-ground mausoleums. Did I spell that right? Which is basically like entombed. In Antarctic ice sheets. I don't think they should do that, especially with global warming. There's 3 options. Storage and decommission. This is dangerous to decommission a power plant, because unless it hasn't been used for years and years and years, you're subjecting people who are decommissioning it, who are taking it apart, to a lot of radioactive wastes. So that's dangerous. That's one way to get rid of a nuclear power plant. Fusion. That's good. Lithium makes water. 1 ounce of fusion fuel is equivalent to 70,000 gallons of gasoline and energy. We don't know how to do this. We know how to do this theoretically. We can do this, but in reality, it's not something we can do easily. Alt energy. You should know the renewable. So, like, highlight this or circle this. Know your renewable energy and your non-renewable energy. So renewable are these, non-renewable are those. Water and biomass, though renewable, are different from solar and wind energy. Solar and wind energy are present constantly. Water and biomass can be depleted and are not automatically renewed. Think about droughts and forests being cut down. Biomass would be like burning stuff, burning trash, burning wood, things like that. So there's a thing. There's another thing. Alternative energies aren't everywhere and are limited. Solar energy. There's passive and active solar energy. This is passive. You can design your house so that it has a wall or a floor room or something like that heats up and it allows the house to be heated. These are best in where it gets cold at night and it's warm during the day, so that you have heat kind of reserved, stored in the wall of your house to heat it up at night when it gets cold. Down here we don't really use these. We don't want it to be hot. Active solar energy systems. This is where we actually change the heat from the sun or not the heat from the sun. We change the energy from the sun into electricity. So the little things on your calculator, those are active solar collectors. Flat plate collectors, evacuated tube collection. These heat up and move a fluid through your house and heat your hot water heater. That's really all these are good for. They don't produce enough energy to run the electricity in your house. You'd need a photovoltaic cell to do that. They used to be really expensive to make. They're not as expensive anymore, and they use those in a lot of places. In fact, there's a grant, which I should talk to you about. There's a grant where schools can apply to get photovoltaic cells put on top of the buildings, so the energy consumption of the schools can be reduced and get free photovoltaic cells installed to help supplement energy. So yeah, heat goes in, something happens, it can be stored as a battery, and then it's sent out as electricity. Power towers. Heats, or the sunlight's sent from these little mirrors and concentrated on one area, heated up. Heat turns steam, turns turbine, makes electricity. That's where it is. It's in Mojave Desert. This is another one where they heat a fluid up in there that does pretty much the same thing. Hydrogen. You can read that. Hydrogen fuel cell. Water. You can get water through a dam or through pump storage process. This is a dam. It's held high. Gravity brings it down. Spins a turbine. Makes electricity. This is a power system. It goes down and then it gets pumped back up. So a little bit of the energy is reserved to pump the water back up to the higher level. This is important. They may ask you what's the negatives of having a dam. So large dams and reservoirs use up land that could be used for agriculture. Dams block migration of fish. Water flowing picks up nitrogen gas, which gives fish the bends and kills them. It's the same thing if you come out of the water from snorkeling or scuba diving too quickly. The gas will actually come out of your blood and make little bubbles, which is bad and hurts. Dams trap sediments. They trap some of the runoff. Large reservoirs increase the amount of water being evaporated, which is bad in arid regions. And this is what happens near Hoover Dam a lot, because it's in a very dry area, and you have this big, large area of water, and that water gets evaporated, where it could be used for agriculture and things like that. Tidal power. This is experimental. So the water comes in. Where's my picture? Water comes in. Let's say it's coming in this way. Comes in. They open up these things. Actually, in Richmond, when I went home for Christmas, they had these near my house on the James River. And what they do is they lift them up, and the water comes in when there's high tide. Then they put the turbines down when it's low tide, and when the water rushes out, it spins the turbines. So let's say they went in this way, and then the low tide comes in, it pulls out, and it'll spin the turbines, which makes electricity. And these aren't used a lot. They're kind of in the experimental stage, but it's using the tides to create electricity. Wind power. Windmills. This is an old-fashioned windmill that was used to make rain. That type of windmill pumps water from the ground for irrigation. Now they're used to make electricity. It's unpredictable. Here's the drawbacks to wind power. It kills birds. Those things slice up birds when they try to fly through them. Windmill farms use a large area of land that can be used for other purposes. Windmills may degrade an area's scenic resources. And actually, I was listening to NPR a few days ago. They were trying to build some windmills somewhere, and some people don't want them in their backyard. They think it'll decrease the property values. So I don't think they're building somewhere around here. So, if you own a house in the nice neighborhood, you have this big windmill stuck in, near your house that degrade your property value. I know, right? Remember, there's drawbacks and positives to everything. And you have to be able to think. You have to be able to separate the environmental positives and negatives and the economic positives and negatives. So everything has both. Everything has an environmental positive and environmental negative, and an economic positive and economic negative. Yeah. There's windmills. Biofuels. If you're just burning stuff, that's biofuels. Here's some examples. Geothermal energy, heat from the ground. That's that. And I'll quickly go over land and water because there's not much left. I'll go over really, really quickly. This one's actually short. Short being 29 slides.